technically, we call an order a topological ordering if for every edge, the vertex it comes from comes in the order before the vertex it goes to. So, for example, a possible topological order here is first A, so first object-oriented programming, then reasoning and logic, then algorithms and data structures, then algorithm design, and then advanced algorithms. And you see that in this order, we do the courses first that are needed in the other courses. So we do object-oriented programming A before algorithms and data structures, because algorithms and data structures needs the knowledge of object-oriented programming. And you actually see that in our academic programming and our academic program, you get these 5 courses in this exact order, which is pretty good by us, I guess. But I guess enough for the compliments, because of course this is not that hard, because of course there exist algorithms to find these orders. So here we see an algorithm to get a topological sorting, to get a topological order using topological sorting. So how does this algorithm work? So it consists of a list, which will be what our order will be stored in, and then a stack and a map. And what we're going to do is for each vertex, we're gonna determine the in degree, so the amount of edges that go to that vertex. And we're gonna store this in our map. So here you see that A has an in degree of 0, so we store a 0 with it. And I has an in degree of 2, so we store 2 with it. And this we do for each vertex. And then if the in degree is 0, then we push the vertex to the stack. So in this case, only A has an in degree of 0, so we push A to the stack. Then comes the core of the algorithm. So while the stack is not empty, we pop the vertex from the stack. So in this case, we pop A from the stack. We add A to the list. We know it can be first because there are no prerequisites, right? And then for each of the outgoing edges, we decrease the in count, the map that we used. We decrease that by 1. So here you can see we popped A, so we make it red because we added it to the list as well, to our final list. And we decreased the value of D and the value of B by 1, so to 0. And now, because we decreased them to 0, we add them to the stack. So if they get decreased to 0, then we add them to the stack. And this basically means we can now do these courses because we have done all the courses before that we needed for this course. So in the next step, we do either of these courses would be fine, but assuming we would put B on the stack first and then D, we of course pop D first. So again, we visit D, so it will become red. We're looking at all outgoing edges. We decrease the vertex where that edge goes by 1, so this will be 1. And if it's 0, we push it on the stack. In this case it isn't, so we don't do that. So we decrease this by 1 and we visit D. Then the stack is still not empty, so we pop B from the stack. And again, we're looking at the outgoing edges and decreasing those by 1 and add them to the stack if they're 0. So both will become 0, so we add them to the stack. So again, we add to the stack C and E. Now we visit E, but that has no outgoing edges, so that's pretty simple. We just visit it. So our current order is A, D, B, E. Then we visit C, and again we check the outgoing edges. The F will go to 0, so we add it to the stack, and the J will not, so we don't. Then we visit F because it's in the stack. And again, we're looking at the outgoing edges. I is now decreased to 1 by D, so we can now decrease it to 0 and put it on the stack. Then we do I, we put H on the stack, we put J on the stack, and then we visit J. So now the order we visited these nodes in is a topological order.